Okay, in this video we're going to talk about electromagnetic waves, which are a whole different kind of class of waves. So previously we were talking about mechanical waves, and mechanical waves need a medium, and they use that medium to transfer energy. Electromagnetic waves are a little bit different, and they actually do not need a medium, and that's because they're self-propagating. So they induce themselves, and they contain their own energy. So when they move, the energy moves with them, and they make themselves move. All kind of complicated, but we can think about this with what we learned in the electromagnetism unit. So over here you go, check out this URL. We have an applet that shows us the electric field generated by a charge. So let it go. You can see it's moving, and you can see these electric field lines. Now, notice if I make the charge accelerate, you'll see these kinks in the lines. And those kinks are what I'm going to call changes in the electric field. It's showing you these distinct changes in the electric field. But if you remember from the last unit, right, and I can also show you that the frequency at which I make this oscillate will give you the frequency of those kinks, how many of those kinks will go by in a second. So if you remember from the electromagnetism unit, we have Faraday's law and Ampere's law. And Ampere's law is telling us that if you have an electric field that varies with time, it produces a magnetic field. And you remember that as a moving charge produces a magnetic field, or like a current produces a magnetic field. So here we go. So here's my charge. I make it accelerate. Boom, I got to change an electric field, but that produces a magnetic field. But that magnetic field wasn't there before. So what I've done is I've changed the magnetic field kind of around this charge. So the magnetic field in this area has now changed. But if you remember Faraday's law, if you have a change in magnetic field, it produces an electric field. Well, now you have a change in electric field because that electric field wasn't there before. But that makes a magnetic field. But that magnetic field wasn't there before, so you've now changed the magnetic field. So you get an electric field. But the electric field, right? And you can do this kind of et cetera, et cetera, et cetera. And this is why if you accelerate a charge, like I've done here, accelerate a charge, you make this change in electric field, and that in turn will make a change in magnetic field, which will make a change in electric field, and that's what it means for a wave to be self-propagating. Once I've created this initial disturbance, this initial change in electric field, the wave will kind of produce itself, and it will kind of expand outwards just from this combination of Ampere's law and Faraday's law. And it's the electric fields and the magnetic fields that actually have the energy in the wave. And so once I produce a wave, an electromagnetic wave, it will kind of continue on by itself, and the energy will be transferred, will travel with the wave kind of by itself without anything interfering. And so that's why a medium isn't necessary. This is a depiction of electromagnetic field, and these kind of light blue lines are the electric field lines that will be produced by an accelerating charge. And these kind of darker blue lines are representing the magnetic field. And if you feel like right-hand ruling it, you can kind of rederive this orientation by yourself. And again, electromagnetic waves have the same property as mechanical waves. They have the wavelength, they have a period, they have a frequency, an amplitude, a direction of propagation. And one interesting thing to note is that the magnetic field and the electric field are perpendicular, and they're both perpendicular to the direction that the wave is going. And you can see that here. And another thing to note is that the different frequencies of electromagnetic waves, so that would be kind of a different frequency in that I'm moving my charge. So if my frequency is like this, I'll make high frequency electromagnetic waves versus like a low frequency one that would be like this. And you can kind of see that in kind of how packed together the little kinks are. So it happens that the different frequencies of electromagnetic waves are things that we actually find quite familiar. And of course, with increasing frequency, they'll have decrease in wavelength. And you'll see that the low frequency electromagnetic waves are radio waves, then microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. And then the last thing is, in the previous video, I've shown you that this equation holds true. The energy of electromagnetic wave is h, Planck's constant, times frequency. So the higher the frequency, the higher the energy.